Okay, good morning. Let's work this problem together. This is a good problem to work. It's very involved, okay? So this type of problem has a number of different things we need to write down first. So I'm going to sort of minimize this and switch to this file over here. And get rid of this. If I can, it's not going to go away, is it? Insert new blank. Right here. Okay, so let me just copy a few pieces of information over. Number one, how much mass of iron. So what are we looking for? Mass. So the first thing I always write down is what M equals question mark. And that's probably going to be in either grams or kilograms. I noticed down here I got grams in this unit. That's a clue. So let's make it grams for now. We can always change this if we need to. What else do we know? I've got a specific heat. That's the C sub P value. Some books don't use that sub P, but it's a capital C. It's called specific heat. It's going to be 0.449 joules per gram per degree Celsius. Both of those, by the way, are in the denominator, the joules, the grams and the degree C. The temperature is changing in this over here. Let's see if I can go back. From 500 to 1500 Fahrenheit. I see the problem already. Hopefully you've already spotted it. But the initial temperature, 500 Fahrenheit. Final temperature, 1500 Fahrenheit. And the formula also says mass C delta T. I need a change in energy here. This is enthalpy or energy, usually defined as heat energy or change in heat energy, sometimes called heat flow, and here it is. It's in joules. Everybody should know capital J is joules. Joules is energy, whether it's kinetic energy, potential energy, electrical energy, or even, in this case, heat energy. Okay? And it's in kilojoules, but I'm just going to write it down like that. 3.56, 10 to the 4th kilojoules, delta H. Now I can maximize this. I wrote too big. When I maximize it, it gets bigger. That's cool. Okay, so these are what I'm looking for and what I know. Second step is write down the formula. So I'm going to put a second column here, although usually on a piece of paper I'd work straight down the piece of paper. Just for your information, I don't like, if you're working on a piece of paper and you're doing one of these problems, just work vertically down the piece of paper. Okay? It's very logical. It's very easy for my eyes to scan vertically down a page. The minute I have to jump left and right across a page, I lose things and I can't follow your train of thought. Okay? So if you're solving a problem on a piece of paper, which you will be doing for me tomorrow, you're going to work down the page as much as you can. If you have to and you get to the bottom, then you can go to the top and make a second column. In this case, I don't have any room, so I'm going to do this. Now I need to solve this for M. So everybody here should know how to solve a literal equation. We're going to divide both sides by what I don't want, which in this case is the C value and the delta T value. If I do that, I should get M equals delta H divided by C delta T. Okay? I'm not going to show you how to do that. Hopefully you know I just divide by C delta T on both sides and I get this for my equation. At this point, I need to figure out if I can substitute things in. Here's my C value. The units are in joules per gram per degree Celsius. The temperature is in Fahrenheit. And my delta H is in kilojoules. So I got to do two things in here somewhere along the way. I need to change joules to kilojoules or kilojoules to joules. And number two, I need to change Fahrenheit to Celsius. Okay? So right here, next to these Fahrenheits, we're going to change those to Celsius. And so to change Fahrenheit to Celsius, I subtract 32 and then multiply by 5/9. And the reason I'm closing my eyes is because I'm thinking 212 minus 32 is 180. 180 times 5/9 is going to give me 100. If that works for boiling point, then that also will work for these numbers. So minus 32 times 5 over 9. And I'm going to do the same thing for this one. Grab the calculator, figure out what that is. 468 times 5 divided by 9. Everybody knows when you multiply by a fraction, you can just multiply by the numerator and divide by the denominator. It makes it really easy. You don't need to know what 5/9 actually is. So this is 260 degrees Celsius. And this one is going to be the same process, 1500 minus 32, which doesn't make much of a difference. And then times 5 divided by 9, 816. I'm being a little bit loose. Now, when you talk about Sig Figs on these problems, don't worry about Sig Figs till you get to your very final answer. Everything in the middle, you can carry out to extra, I won't mark off, you can carry out to extra digits. In fact, if you round off every single number in a problem before you get to your final answer, you're going to be piling up a whole bunch of errors. Every time you round off, you lose a little piece of the puzzle. And if I rounded these off too much, and then I rounded off the kilojoules too much, and then I got to my final answer could be off by 3, 4, 5, 6% because I've rounded everything off along the way. So the only place I need to worry about Sig Figs is when I get to my final answer, okay? So I'm okay carrying some extra Sig Figs in the middle here. Okay, delta T is going to be this minus this. C value is going to be this. Delta H, let's change that into joules so that it cancels out with these joules, okay? Right now I've got 8 kilojoules down here. So I'm going to put that right underneath here. If this is in kilojoules, we're going to multiply by a conversion factor of 1,000 to 1 to change it to joules. There's 1,000 joules in 1 kilojoule. So that's going to increase that by a factor of 1,000, right? Easiest way to do that is just increase this number by 3. Thank you, Ben. So 3.6 times 10 to the 4th becomes 3.6 times 10 to the 7th kilojoules. No. Joules. Okay? So now I've got joules, I've got Celsius, I've got joules, grams, and Celsius. I've got grams. All my units are kind of ready to go. We're ready to substitute into this equation. So we've got M equals delta H over C delta T. M equals 3.6 10 to the 7th. Divided by 0.449 times 816 minus 260. Now the order at which I subtract these, and that's degrees Celsius. The order, if I take 260 minus 816 or 816 minus 260, isn't going to change the numerical value. All it's going to change is whether it's negative or positive. And if you really think about this type of problem, all it's telling me is whether this is heat being added or heat being subtracted. In other words, I'm not worried about a negative sign in this case, okay? So, M equals, calculator, clear. And make sure you bring a calculator tomorrow if you don't have one today. 3.6 EE7 divided by 0.449 divided by 756, 746. Anybody know?
Why are you dividing the 816 minus 260? Like the 0.449, you said divide that by the 816 minus 260.
Say it again.
I said you just said divide 0.449 by 816 minus 260.
No. I said 3.6 times 10 to the 7th divided by 0.449, and then I said divided by this. When I punch things into my calculator, I'm going to divide by anything in the denominator, right? Unless you use parentheses, your calculator won't understand what's in the numerator and what's in the denominator. So literally in my calculator, it's 3.6 second EE7. divide, hit the divide key, 0.449, hit the divide key again, this number. If I put a multiply in there, it's going to think this is up here, your calculator will. Because your calculator, every time you hit a function key, add, subtract, multiply, or divide, it does an internal subcode. Okay? What is 810? Never mind, I'm going to have to start over again here. 816 minus 816 minus 260, 556. Okay, so final answer here, 3.6. EE7, divide by 0.449, divide by 556 equals 144,205. Joules cancel out, degrees Celsius cancel out. I have grams in the denominator of the denominator. Okay, so again, that's a complex fraction, which means the grams end up being in the numerator, which is what we need. So that's nice. Now we worry about sig figs. Okay, and I got 144,205.3484161446. And if you write that down, I'm gonna laugh when I grade your paper. Okay, so we got shit. I mean, you see something like that long, it's like, oh no. I need to do something about sig figs. So I'm going to go back to my original information here. Okay, this is definitely 3 sig figs, but it's a constant. You can consider that as a constant because it is a specific heat. It's a number we would look up in a book for whatever this metal or material happened to be. So that's kind of a constant. I'm going to kind of ignore that one. My delta H value is definitely 2 sig figs down here. And these temperatures would be 1 sig fig and 2 sig figs, kind of, I think. Temperatures are always tricky. Let's see how it's. They're pretty exact. I'm going to call these numbers call these numbers 3 sig figs and 4 sig figs, and let me explain why. Remember that your sig figs always go back to the piece of equipment that you're measuring something with. And what we're talking about here is probably 2 numbers that were measured with a thermometer. The thermometer is generally plus or minus a degree. My guess is that if this was not meant to be 500 exactly, they would have written 498. If this was an actual measurement from a lab, it would probably been 498 or 502. So I'm using a little bit of grain of salt here when I look at these temperature numbers. It's not like I have a thermometer in front of me and I can actually measure. But I'm guessing these are accurate to 1 degree. So I'm going to call this 3 sig figs, 4 sig figs, and 2 sig figs. In either case, this one's going to be the controlling factor. So this has to be rounded off to 2 sig figs. So we're going to call it 1.4 times 10 to the 5th grams. Yeah. And did it ask for the information in grams or kilograms?
No, megagrams.
Put your answer in megagrams. Oh my goodness. Okay, so we're not done yet. So go back here. Times. So we get our Grand Monarch King Henry. So we're going from grams to decagrams, hectograms, kilograms. That's 1,000. To megagrams, that's another 1,000. So I've got 1 million or 10 to the 6th. 1 megagram is 10 to the 6th grams. So I'm going to divide that by 10 to the 6th, and we're going to get 0.14 megagrams. Not magnesium, by the way. Just what Mg looks like. Okay, so I've used my King Henry. We've used some temperature conversions. We've got some standard conversions from joules to kilojoules. We've got a formula that we substitute stuff in here. This one's a pretty involved problem. Take it step by step, working through. Questions? Chelsea?
You said with temperature, you took it as 3 and 4 sig figs. So does that mean any temperature we get, however many numbers are there, or how many sig figs there are? Like
Perhaps.
if I had 8,000 degrees, that would be 4. As long as it says degrees, I'd be counting those numbers as well.
I don't know. I'm just kind of relying on a little bit. In this case, it doesn't make any difference. So feel free to ask if it comes up during the test. Okay?
Okay.
Feel free to raise your hand and ask, and I'll try and guide you.
Okay.
Again, sig figs are important for measured quantities. Things on scales, energy from a bomb calorimeter, which you don't know what that is yet, or maybe you do. Things that are measured. And so you always have to think about how is this measured. And again, this number, this C number, is something I would look up in a book like my big handbook of chemistry and physics down there, and it has a C values for millions of different things.
Mm-hmm.
And you actually look it up, so it's considered to be a constant. Do I expect you to know that that's a constant? No, maybe not. Okay, so again, it's okay to ask certain questions like that if I haven't indicated in the problem. Okay, put your bell workbook away. This is a great one. I'm glad we went over it. I intended to go over that. Let's go ahead and take a look at the homework questions from last night. Okay, I gave you 6 problems last night to do, and they weren't really problems. They were pretty quick. And okay, let's look at the addition and subtraction ones. I had a couple questions before school about this, and I'm glad somebody brought it up. Did I give you, which ones?
41.
Okay, let's cover 41. 41 says add the following numbers, 414, 7750, and 2500. Now, I'm glad this one came up this morning. So when we add and subtract, yes, that's 3 sig figs, that's 3 sig figs, that's 2 sig figs, but that's not what we're worried about, okay? When we add and subtract, we're worried about precision. So in this case, where I have big numbers, I'm going to kind of treat these zeros, since they are placeholders, as unknowns. Kind of like when we had the decimals. If I called this 0.414, and if I had 0.7750, and if I had 0.25 or whatever, remember how I put the little question marks in here, right? I'm going to treat these zeros as question marks because they're placeholders. This is really only 2.5 times 10 to the third. This is really 7.75 times 10 to the third. I'm not sure about those last digits. So I'm going to treat these like I did when we did the decimal problems as question marks. So when I add these together, I still get 4, but that's going to be a question mark. And here I'm going to get 6, but it's going to be a question mark. And then I have 7 plus 9 is 16, and 8 plus 2 is 10. So it is 10664, but those last 2 digits I'm not sure about. Because again, I'm adding a number that's known to a number I'm not sure about. It's uncertain. So in this case, I'm going to have to round this off to this place right here, the hundreds place. Since this is a 6-4, it is going to round that 6 up to a 7. Okay? There is at least a 6 and a 4 there. The problem is I don't know how much bigger they are, but no matter what they are, it's going to round this up to a 7. Okay, so your answer should be 10,700. Or you could call it 1.07 times 10 to the 4th. Your choice. Destiny, question?
Oh, okay, never mind. I
Okay.
got it.
Melody.
I know the zeros are placeholders, but why do you put the question mark on them if they're? I just don't get it.
We don't know if they're zeros or not. Okay, the fact that something is a placeholder tells me I'm uncertain about whether that's actually 0 or some other number. Okay? I'm going back to the illustration I used in class. If I called the Bureau of Statistics in Alabama and said, what's the population of Alabama today? They'd say 5,432,000. Yeah. What are they saying? They're saying it's somewhere between 5,430,000 and 5,440,000. They don't know because some people died, some people were born, some people moved out, some people moved in, and some people were abducted by aliens. Okay? So we don't really know. So those last three digits, the 000, are uncertain. And it could be anything. So it's the same thing here. We really don't know if this is 2,400 or 2,600 or somewhere in between. So it's 2,500. We really don't know if this is 7,740 or 7,760. So it's somewhere in between. Okay, that last digit is our uncertain number. So I'm going to treat them just like when we did the decimal problems as unknowns. I'm going to put a question mark on top of them, and that means 4 plus an unknown number is an unknown number. And 1 plus 5 plus an unknown number is still an unknown number. I can't be certain what these digits are. Okay? Careful with those ones. Number 43, we're multiplying. So 24.8 times 6.4 times 301. Let's pick on Reagan. How many sig figs on the first one? How many sig figs on the second one? How many sig figs on the third one? 301? 3. Okay, so my answer has to be limited by this one. So once I multiply all three of these numbers together, I don't have the answer. Ben, George? No? Chase?
48,000.
48,000? No? You gotta make me.
Oh, that's what I got.
Okay, here we go. 24.8 times 6.4 times 301. Okay, 48,000. Yes. Okay, so we're going to round it off to 2 sig figs because of the second number here. You can call it 48,000 or you can call it 4.8 times 10 to the 4th. Okay, both of those would be acceptable. Okay, the rest of that is 47,774.2. But again, we're going to round that up to 48,000 for the 2 sig figs. Okay, let's do that last one there. Last one is 5.905 divided by 14.0. Peyton, how many sig figs in the top?
4.
How many sig figs in the bottom? So my answer can only have 3 sig figs. Okay? Got the answer? Make me do it. 421,786. 421,786 is what the calculator thinks, and we're going to limit that to 422. Right? All right? Okay, always round. So go ahead and punch the numbers into your calculator, and then look at how many sig figs your answer should have. It's not going to be 4, it's going to be 3. And then round it off. The chapter in the book has rounding rules. I passed right over them very quickly. You should know how to round things off. Okay? It either rounds up or it stays the same. You never would round this down to 420. It's either going to be 422 or 421.
I want 14 plus 0 to be 2 sig figs.
Because of the decimal. Because this decimal tells me that I can measure this to the tenths place. It tells me I'm positive it's not 14.1. It tells me I'm positive it's not 13.9. This is 14.0. Remember, go back and look at those rules for the sig figs. Rule 1 and 2 are very logical. Rule 3 and 4 are the tricky ones. It has to do with any zeros to the right of the decimal. Okay, and it makes a difference. Remember, if I have this number, this is a crazy number, right? So these numbers are placeholders, and these numbers are all significant. And you need to know that, okay? It's trailing zeros to the right of a decimal are important. leading zeros or not. Why? Because I can actually change this into scientific notation. 3.0 times 10 to the, it'd be 3.00000. I actually can measure, this number says I can measure all the way out to that place. But in this case, it's going to be times 10 to the negative fifth. Okay, placeholders in front, trailing zeros are significant. On big numbers, 564,320,000, these are placeholders. These are all significant. These are non-zero digits or zeros in between non-zero digits. Rule 1 and Rule 2. Rule 4, these are called placeholders. Placeholders, PH for short, placeholders. Okay.
Can you go back to the last slide?
This one.
No, the one. Okay, so 1.07 has 3 sig figs, right?
Yes.
And then 2500 only has 2, right?
Right.
So why would our answer have 3 sig figs?
Because there's different rules for multiplication and division than there are for addition and subtraction. 2 separate rules, okay, which I cover in the notes. Be very careful. When we multiply and divide here, this is division, so I'm limited by the 3. This was addition. So again, when we add and subtract, it's not 2, 3, and 4 sig figs or whatever. It doesn't matter how many sig figs there are. We actually line up the decimals and figure out what are we uncertain about. It has to do with the precision of the numbers that we're actually adding and subtracting. So it's a different operation. It's literally a different rule. And that is one of the most common errors. Please, everybody make a mental note. Different rules for addition and subtraction than for multiplication and division. There's only one rule for each of them, but okay? Fewest number of sig figs for multiplication and division, and when you add and subtract, you have to line them up and say, what am I sure about? Thank you for asking that. Good point to clarify. Okay? And again, down here, this was multiplication. So it was 2, 3, 2. We're worried about the 2. Multiplication, division. Okay, I want to look at the front side here. We have a couple of these. I think number, which ones did I give you?
10 and 12.
10 and 12? 12? Man, we already did that one. Okay, 690 plus 273, right? You should have that answer already. How many meters in 89 inches? This is a simple conversion, okay? So 89 inches, put it over 1. There is no math, there is no formula. This is a simple conversion. So there's 2 types of problems we're solving here. Conversions, word problems, and then the conversion word problems combos. Okay, so in this case, 2.54 centimeters in 1 inch, and we're changing this into meters. The goal is to make sure all of these units cancel out. So once I set it up, make sure my units cancel out, inches and inches, centimeters and centimeters. Make sure my conversion factors are right. There's 2.54 of these small centimeters in 1 inch. This one, 100 small centimeters in 1 meter. Okay, always think how many of the small ones are in the big ones. Get your King Henry out. Always small at the bottom, big at the top. And then get your calculator. 89 times 2.54 divided by 100. Anybody got the answer? 2.26. Thank you, Ethan. I'm going to keep this on a conversion factor like this. We always go back, these are considered constants. We always go back to our original number, 2 sig figs here. So 2.3. Jackson?
Yeah, 2.1.
Try again.
How the same thing you did? Yeah.
89.
Times 2.54 is 100.
2.2606. Should round off to 2.3. Check your calculator. Make sure you punch the things right. Make sure also your calculator doesn't have your, sometimes you can set your calculator to limit the number of decimal places. Okay? And if it's limited to 1 decimal place, it might be rounding this off or something like that. Okay, look over the sheet. Any other questions on here? We could do more problems. Let me do number 44 real quick. This is a good practice problem. It says, what is 2.66 times 10 to the 4th? And we're going to subtract 1.03 times 10 to the 3rd. Now remember, when we have this type of problem, we can't subtract until we get the same power of 10. Because if I try and line these up, this would be 2, 6, 6, 0, 0, and this is 1, 0, 3, 0. So really, I can think of it this way. Minus, you can actually do it this way, in fact, okay? And you can subtract those two numbers. But if they're really huge numbers or really tiny numbers, you're going to need a better system than writing out those huge and small numbers. In this case, you can see the Sig Figs last digit here. You can do this on your calculator. But what I want to do here is I want to change this number to 10 to the 4th. So if I change that to 10 to the 4th, it's going to decrease. If this goes up, this goes down by a factor of 10. Every time I increase this number by 1, this goes down by a factor of 10. So this is literally 0.103 times 10 to the 4th. This is the same number. So if I know that, then I can say 2.66 minus 0.103. Both of those are times 10 to the 4th now. And now you can see that I have a question mark here. Okay, some number minus 3, 6 minus 0, 6 minus 1, and 2. And the fact that I have that question mark right there tells me that's not going to be a significant digit. I can't include it in my answer. So this is my answer here, 2.56 times 10 to the 4th. And these ones can be a little bit tricky with the scientific notation, adding or subtracting. Just don't jump to conclusions. Either line it up like this, which again, we're saying this is a placeholder. So you get the same answer in both cases, 2.56 times 10 to the 4th, or 25,600.
Now that's the same answer if you change it back. But do you prefer us to change it back to like 10 to the 3rd, or do you want us to keep it power?
Yeah, you could.
Or do you not care?
10 to the 3rd.
No,
If I-
like if we change that back to 25.6 to 10 to the 3rd, which one would you prefer us to put it in?
The correct one. And the problem is, this is not proper scientific notation. That coefficient always needs to be between 1 and 10.
Okay.
Okay. It's not. It's mathematically correct,
Okay.
but as far as scientific notation goes, which we did cover in this chapter, it would be incorrect. So you would always go to a number between 1 and 10 times 10 to the 4th. And there's exceptions to that rule when you're trying to use that number to do something else for scientific notation purposes. Okay? Okay, we're just going to run real quick through the chapter here. Just a quick review. There are other things in this chapter that you need to know. So this is how the test is formatted. I have a multiple choice section on the Chromebooks. Approximately 40 questions. I don't think it'll take you that long. And then I think I have 5 mathematical problems which you will work on paper for me afterwards. Okay, so as soon as you finish the Chromebook, you're going to close it down, and I'll give you a sheet of answer paper, and you will do your work on that paper. But I do want to make sure we don't forget about a bunch of stuff here. So, number 1, the SI system. Everybody should know what SI stands for. Everybody should know these base units and what they are and where they come from. We had that question about the cesium atom radiation. What is that related to? Yes, the second. And then we had something about, 1/299,300 and something of a second, the amount of distance a light travels in a second. What is that, Jackie?
Meter?
That's a meter, okay? And then just last year, they changed something so that now it's related to a constant that's known as Planck's constant. And that was the other one.
Kilogram.
The kilogram, good. Okay, so all of those, all of our three bases, the kilogram, the meter, and the second are now related to physical constants. We covered them, we talked about them. You should know about the Kelvin scale and how to get Kelvin to Celsius and Celsius to Kelvin. You should know this system. Again, I might ask you a question or two about it, multiple choice wise, but you need to know more than that how to use it. We've been using it all week long to solve these other problems. Okay? Any questions about the King-Henry system? It is on your periodic table, so if you do forget, okay? Sometimes you don't realize how much we've covered in a week and a half until we go back through this stuff. It's like, whoa. Second, the meter, the kilogram, Kelvin scale. We talked about Celsius and Fahrenheit. And Kelvin and Celsius. Derived units, everybody should know what a derived unit is. It's derived from our base units. Things like density, which we did a lot of problems with density. Don't be surprised if you see another one. And volume is also a derived unit. We did some practice with these. Everybody should know the first letter is your King-Henry prefix, and the second letter is a base unit, or a derived unit. Okay, in this case right here where we have liters, that's a megaliter, right? And so the second letter can be a base unit, or it can be a derived unit. And we went through a whole bunch of these. By the way, I don't know, I think first period we never did the middle ones here. That little guy right there is called omega, so that's an ohm, which is an electrical unit of resistance. And this is an amp, just by the way. Capital A is amperes, which is a measure of electrical current. And then capital V, of course, is volts, voltage. Millivolts, megavolts, kilovolts. Anybody in robotics, you'll see those terms a lot this year. Okay, these are your unit conversions from SI to English. They're on your sheet. Yay. Okay, let's zip ahead here. Scientific notation. We spent quite a bit of time talking about how to work it, add and subtract these numbers. Review that, please. Okay, I'm not going to spend a lot of time on it because I think you're pretty familiar with it. Calculator, make sure you know how to use that double E button in case you need to. You will all year long. Conversion factors and dimensional analysis. Okay, that's what we've been spending a lot of time on working these problems the last 3 days. And if you come to the review session tonight, that's pretty much what we're going to do. We're going to work a few problems together. I assume everybody can study King-Henry and memorize things at home. I don't spend time with you memorizing stuff. Usually just spend time working problems.
Yeah, they got the, we're all elected.
Thank you. These are very valuable. I would suggest you find a way to make a copy of this, download it. You have it on the Remind system now, and it's also on the Portal system. So again, I didn't print these out for everybody because it's a 3-page color document, but this is the first page, second page, and third page of how to solve these problems. And I'm very specific that you follow these procedures, okay? This is exactly how I've solved every problem in the last few weeks. What are we looking for? What do we know? What formula do we use? Do we need to rewrite the formula? Substitute in the formula, cancel out units, check your Sig Figs and your units, and put a box around your answer. Okay? Second type are simple conversions like the one we just did. This one converts, for instance, the speed of light in meters per second and the speed of light in miles per hour. And then this is the kind of problem we did for Pell Work today, where you've got a little bit of everything going on, okay? I've got conversion factors in the middle, I've got a problem I need to solve using a formula. I need to know a little bit of algebra on how to rewrite that formula. Lots of little pieces of the puzzle to fit together. Also in this chapter we covered error and percent error. We did some bell word questions like this yesterday. So the error and percent error and accuracy and precision. Again, I'm not spending a lot of time reviewing this. You might want to read that section of the chapter, just review. There will be some questions about accuracy and precision. At the end of the chapter, there's some really good review questions that give you a set of data, and they say, is this data accurate or precise or neither or both? Okay? And again, you look at how close the numbers are together. Are the percentages all about the same? Percent error, is the percent error really tiny or is it significant? 50% error is horrible. 10% error is iffy, and less than 5% error is usually pretty good. And then we talked about the formula for percent error. We want to know this. Okay? I probably won't give it to you. It's something I expect you to have memorized. So it's experimental minus accepted divided by accepted value times 100. And we did some problems earlier this week with that. Sig Figs. Okay, and we spent quite a bit of time on Sig Figs, practicing these. The more you practice, the better off you get. If we have a minute or two here, we'll go back to the end of the chapter. This will be a few questions at the end of the chapter. And the last section of this chapter was graphs. This is a long chapter. There we go. And section 4 is graphing. So make sure you know how to use the 3 types of graphs: circle graphs, bar graphs, and line graphs. Okay, know the situation for each of these. We use line graphs for comparing 2 variables. We use circle graphs where we're comparing the part to the whole, percentages usually. And we use bar graphs to compare characteristics of things or things that we can count. And we covered all that in here. We looked at examples of each. We talked about different aspects of a graph: title, axes, units, best fit line, how to calculate slope, all that stuff. And I did have a little mini lesson planned for earlier this week about how to use Excel to create a graph. We're going to save that for next week or the week after, because Wednesday was kind of a bust. Okay. And that was the end of the chapter. Good. Grab your textbook real quick. Let's take a look at a couple things here at the end of chapter 2. Page number 62 and 3. There are a lot of great questions here. I haven't given you even half of them, okay? So again, look through this end of chapter assessment here, and there's some great review questions. You ought to be able to answer just about everything. Number 81, 82, 83, and 84. I think I assigned them for homework and I never checked them, okay? If anybody wants the answers to those, why don't you jot them down right now? And you can go back and check your homework. If you have questions, you can see me tomorrow morning before school or tonight at the study session. Number 81 was $18 per gram. Number 82 was 1,810 kernels of popcorn. Number 83 was 1.34 milliliters of oxygen per gram of hemoglobin. And number 84 was 1 liter of milk. You'll notice on number 91, round off to the number of Sig Figs. 4 Sig Figs. Let's do a little bit of that. Let's jump to Sarah Hagar, number 91A. Round that off to 4 Sig Figs for me. To the who? Second? That'd be 431, but we need a few more 10 to the somethings in it. So you put the decimal between the 4 and the 3. How many decimals did you move? 10 to the 5th. Okay? 4.318 times 10, or actually Yeah, 4.318 times 10 to the 5th. Or you can say 431,800. How about B on that list? You got it open, Connor?
10,300, 10,240.
Perfect. 10,240, rounded off to 4 sig figs.
You have to put it inside the indentation.
No, the book does a lot, okay? Again, most of the time, this is not the final answer. You're going to be using this to do something else in a problem with it. But no, you can do it either way. Katie, how about letter C? Perfect. 1.035. How about letter D? Aiden? Caden? Aiden? Aiden. You're so quiet back there, Aiden. Mr. Kraft.
I got 0.0043 centimeters.
004 what?
3.
No. Somebody want to fix that one for me? Chase?
0.0044.
No. Those are only 2 sig figs, both of you. Remember, your leading zeros are not significant. So in that case,
I just have a question. Did you say we do not have to put it in scientific notation?
I'd accept both. Yeah. Yeah. I mean, 1.035 is what Katie said letter C was. I wouldn't put that in scientific notation. I could. 1.035 times 10 to the 0 power. But why would I do that? So you can do it either way. Okay? On letter D there, guys, remember, 4 sig figs means 0.00. Those two are not significant. 4, 3, 8, 4. Okay. Have a great day. You're dismissed.